Yeah. My presentation is a future sales estimation using patent. Let me introduce myself. I'm Koichi Kamijo from Japan, and I'm in International Professional University of Technology in Tokyo, Department of Information Technology since last year. And I used to be in IBM research for until last year. Okay. And the goal of this paper is very simple. It is to estimate the future sales volume of the pharmaceutical. Actually, it is a long way to accurately estimate the volume. So we focus on how we can improve the estimation accuracy with various methods, including pharmaceutical information and patents for them. Then, why did I choose pharmaceutical? This is development of pharmaceutical often takes a long time. For example, 9 to 17 years. And development costs are very huge, like over 5 million, 500 million US dollar. And because of COVID-19 pandemic, demand of vaccines are very increasing. These are the reasons why I choose the pharmaceutical. And for currently, estimating a pharmaceutical sales volume requires several steps, such as knowledge of the disease and the pharmaceutical market, and comprehensive understanding of the domestic and global regulatory environment and market access. So this task is often performed by a company with appropriate expertise, such as Clarivate. However, outsourcing such estimation is typically very expensive and requires much cost. And we need to share some sensitive information with the contracting company. So accordingly, it will be desirable to make sales volume forecast in-house without such exposure. So any method with non-expert can estimate. Possible estimation approach is one of the possible estimation approach is to estimate from the name of the developing company. And another piece of useful information is when, that is, which year and which month the pharmaceutical is initially developed. This figure shows the sales volume values from each pharmaceutical development company for the year 2019. Although this figure shows the sum of multiple pharmaceutical for each company, since the sales volume values are different from the different companies, by knowing the development company, we may be able to roughly estimate the future sales volume of each pharmaceutical. So we could also use additional information such as the name of the sales companies, but these companies may not have been decided at the time the pharmaceutical was developed. So we used only the development company, not the selling company. Also, as the year the pharmaceutical was initially developed, we used the year of the first patent application for the pharmaceutical was applied for a patent office. Another possible source for sales estimation is the patent applications. For almost all the newly developed pharmaceuticals, they apply for patent. So if we can make a best use of the patent, it may improve the sales estimation accuracy. So usually a patent include title, abstract, filing date, inventor's name, reference cited, and citing figure, claims, description, and so on. For example, left the information which may be variable for sales estimation as a patent attribute, such as word count of title, word count of abstract, word count of document, and the number of claims, which are relatively easy to obtain. However, it is possible that by analyzing patent itself, that is, what are written, which words are used in a patent, how much hot words, such as those used in the pharmaceutical articles as well, are used in the patent. Estimation performance will be improved. In this paper, we estimate the sales using not only the patent information, but also the patent content, such as words used in the patent, including hot words as well. Again, in summary, we did sales estimation with these five stuff. A is the information about the pharmaceutical. B is the information about the first patent of the pharmaceutical. The C is the words used in the first patent of the pharmaceutical. And the D is from C plus pharmaceutical related articles. The E is a combination of all A from D. And we evaluate the sales estimation performance. And this figure shows our research framework. So our goal is to construct a model that can estimate the sales volume of a new pharmaceutical on the basis of not only the name of the development company, but also patent and articles related to the pharmaceuticals. And I'll explain each step in detail later, but I'll explain the overall research framework by this figure now. In this figure, I explain four kinds of estimation, A, B, C, and D, which I already explained in the previous sheet. We obtain the pharmaceutical list and sales volume from a database expert company, which will be introduced later. This is 1 and 2 in this figure. And first, we estimated the sales volume by using the information about the pharmaceutical, especially just from the name of the company that develops the pharmaceutical and the year of the pharmaceutical was developed, which we use the date, the year, the first patent application for the pharmaceutical was made. This is A. And for each pharmaceutical, we collected the first patent application from a patent database, that is 3, and estimated the sales volume using the information about the patent, that is B. And we next performed the morphological analysis for each patent, that is 4, and estimated the sales volume from the usage ratio of each word, that is the number of appearances of each word divided by the number of the appearance of all of the words in each patent specification, that is C. Next, we collected the articles related to the pharmaceutical, that is 5, performed morphological analysis on them, that is 6, and calculated the term frequency, inverse document frequency, that is particular TF, IDF, of each word in each year, that is 7. Then we calculated the sum of the usage ratio of each word weighted by the TF, IDF each year, that is 8, and estimated the sales volume, that is D. In addition, we did estimation using all of the combination of A through D as an E. So in our model, for each estimation, we use a deep learning, that is 9. And for evaluation of the sales estimation, we use leave one out, that is LOO cross validation, that is 10, which will be explained later. Regarding the data source, we obtained the pharmaceutical list and sales volume from a database called Cortelis, and the patent database from Darwin Innovation. Currently, both are now run by Clarivate company, whose employees include the experts on the pharmaceutical and patent. And for patent, we only use those compiled with PCT, that is Patent Corporation Treaty, written in English only, to ensure the unified patent format. So this page shows a quick summary of our approach to estimate the sales of the pharmaceuticals. We first collect the pharmaceutical, that is DI, for which both of the sales volume data and the first patents for DI are available. For sales volume data, which we call SI, I is the name of the pharmaceutical. We use the sum of the sales volume from until 2019 plus some estimation value by expert until 2027. It may look that the inclusion of the expert estimation is somewhat invalid, but pharmaceuticals developed just before or after 2019 do not have enough sales data. Estimating these values still has worth for research in that we estimate the sales volume. For the patent, although it is usual that several patents are filed for one pharmaceutical, we use the first patent for each pharmaceutical since we'd like to evaluate how much it is possible to estimate at the year the pharmaceutical was developed. To estimate the sales of the pharmaceutical DI, we use the pair of the patent and sales except for DI itself. And we also use AI, that is a patent for I. Then we evaluate the difference between the actual sales SI and estimated sales we call SI hat. And this figure shows a plot of the sales volume of pharmaceutical used in the experiment. This is the y-axis is in million of US dollar from 2019 to 2027 by Claribet, and smallest first. And the left side figure shows the real data, and the right side figure shows the logarithm of the real data. Clearly, loads sales volume are well distributed and linear, and it is expected that we can make a more accurate estimation compared with the case of the real data. So for the model construction for sales volume SI of the pharmaceutical DI, we used log SI instead of SI. From now, I'll explain each method step by step. First is the information about the pharmaceutical, which is company name and the date of the year of the pharmaceutical was first developed. Regarding the company name, we use one hot vector, and regarding the year of the pharmaceutical was first developed, we use the year when the first patent was filed or applied to a patent office. We input this vector to a neural network to estimate SI. And this figure shows an example. And as already explained, patent specifications usually consist of a title and abstract claims and detailed explanation and so on. We analyze the correlation between those components and the sales volume and examines the sales estimation obtained with these parameters. We used word count of title, word count of abstract, word count of document, and number of claims, since this information could be obtained stably from any patent. Next, we estimated sales using the word used in the first patent of the pharmaceutical. However, millions of the words would be used for all the patents to be analyzed. We need to pick up the words that may contribute to the estimation. With that in mind, we first analyze the correlation between the words used in each patent and the sales volume of each pharmaceutical. For each patent specification AI for pharmaceutical DI, we counted the usage ratio of each word and divided by the total count of the words in the patent. We defined the usage ratio of each word UWI. Therefore, adding all UWI over double will be 1. And we excluded the stop words, numbers, and symbols, and the case, and also it is case insensitive in the calculation of the usage ratio, but included all the other words regardless of the part of the speech. We also use a word from all the pages in the patent, regardless of abstract claim or description. We then define the vector U double hat for each word double as equation here. So, and selected the set of words that have not small absolute R value, which is equal to or more than larger than 0.1, and a small p value, which is equal to or less than smaller than 0.01. And here, omega is the set of words satisfying these conditions. Then we define the x3, xi3 in the lower right of this page. Then for each xi3, it is inputted to the neural network as this figure, and output is the sales volume, actually log SI. So for morphological analysis, stemming and lemmaization, we used free word tokenized package in the NLTK package. And in this package, for example, we were performing the mass maintenance. It rains and cat and dogs are converted to we were perform maintain. It rain cat and dog. So some words are not included in a normal dictionary, like a maintain. So this table shows an example of the words that satisfy R value is absolute R value is more than 0.1 and P value is less than 0.01. And we sorted by the absolute R value. And in this figure, ratio is the ratio of the patents that used at least once out of the 423 patents used in our experiment for each word. So, and bold words in the table are related to the pharmaceutical or disease. And this table shows that 36% of the words were related to a pharmaceutical or disease. Those R value is plus means that these values may contribute to the increase of the sales, and minus in the R values means that it may contribute to decrease. And if a patent includes the hot keywords that reflect the high popularity of the pharmaceutical at the time an application is made for the patent, the sales volume of the pharmaceutical may grow in the future. With this in mind, we weighted the word usage ratio in the patent specification based on the usage of each word in pharmaceutical-related articles. For the analysis, we first collected two kinds of pharmaceutical-related articles published periodically. One is a Pharmaceutical Benefits Pricing Authority Annual, issued in Australia since 1998. The other is the Pharmaceutical and Medical Devices Agency, issued in Japan since 2009. We used these articles up to 2020. And using the pharmaceutical-related articles, we calculated the TF-IDF of word W used in the article for each year Y. To do that, for each word W, we counted how many times W is used in all of the articles issued in year Y, and divided by the number of the old words as TF-WY. We then checked how many times W is used at least once over all of the years through the year, and as DF-W, then calculated the TF-IDF as equation 7 in the right-hand side. Below the blue line in the bottom is an example of the W2 for TF and DF. For each pharmaceutical DI, we calculated the sum of the word usage ratio in the patent specification AI, that is UWI, weighted by the TF-IDF y for each year y as equation 8. It is possible to increase the UT weighting ratio in the model whose year of the first patent specification application, that is Y0, is close to the nearest article publication year. But in deep learning, such a weighting ratio is automatically adjusted. So from this viewpoint, we evaluated the case of the putting the element UTS, UTS, so that the position of each element for the year the article is published minus the year the first patent is applied, that is YPI, is the same for all IIs. Toward this, we created a new vector xi4 by padding the zeros to the left and the right as xi4. We evaluated the sales estimation performance of each of the methodologies discussed in the previous sections. In this experiment, we used n equal 432 pharmaceuticals whose sales volume SI and the first patent AI were both available. Since n equal 432 is not sufficiently large, we evaluated the accuracy of the performance using the LOO cross validation. We then evaluated the performance of each method by RMSE and MAE, that is root mean square error and mean absolute error. For the estimation model, we used a keras regressor and multiple regression with two hidden layers, 128 nodes with a little activation each, and the number of the epochs is 100, unless specified otherwise. So we used the mean square error for the loss and Adams for the optimizer, and we normalized the input vector by Z square normalization, except for the one-hot vector. To speed up the experiment, we used the Google Collaborator TPU. For Pearson's R-value calculation, we used R-value threshold 0.1 and the p-value threshold for 0.01. Then we had the 866 was satisfied with threshold, which means that the size of the omega is 866. And the left-hand side panel of this figure shows the number of the companies that develops one or more pharmaceuticals. And the total of 432 pharmaceuticals was considered in this experiment. And specifically, 186 companies, that is 43%, developed only the one pharmaceutical. And one company developed the 13 pharmaceutical, which is the highest number of pharmaceutical developed by the company. And actually, name of that company which developed 13 pharmaceutical is Eli Lilly and company, and for 11 Genetics Inc. and GlaxoSmithKline Biologicals. And the right-hand side panel of this figure shows the number of the first patent application in different years between 1980 and 1921. And this table shows the experiment result. Number one is a case of using company name and the year of the patent applied. The number two is a case of using the first patent information such as word count of title, word count of abstract, word count of the document, and number of the claims. Number three is a case of using the words used in the patent application. And number four is a case of using hot words used in the pharmaceutical articles as well as used in the patent. And of course, regarding the RMSE and MAE, smaller the better. The most right column is the ratio where the ratio between the actual and estimation sales is smaller than 2, which means that between 0.5 and 2. And similar inference can be made from the experiment result. For example, a combination of number 134, input 134, that is number 6, yielded the best performance for RMSE and MIE. And one interesting fact is that while performance of number 4, that is just using hot words, was not as good as number 3, that was using words in patent. It helps to improve the combination 1 and 3, that is number 5, to 137, that is number 6. This implies that the patent containing hot words indicates that high potential for the future sales volume of the pharmaceutical. And this figure shows a scatter plot of actual, that is the x-axis, versus estimated, just the y-axis sales in log order in a million of US dollar from 2019 to 2026. And the diagonal line shows estimation equal actual sales. And the left figure shows the case of just using the company name and patent applied year. And the middle figure shows the word used in the patent. And the right figure shows the case of the combination of all these stuff. And we can observe that from the right figure, in the right figure, the plot are getting closer to the diagonal line, but we still have the room to improve. And we also evaluated the RMAC and MIE and the ratio of the estimation divided by actual within 2 times, but by changing the number of the epochs and the node size with combination of the 134, that is the combination of all the stuff. And the left graph shows the difference by the number of epochs. That we can observe that RMSE and MAE improves as the number of epochs increase, but the performance remains unchanged or decreased as the number of epochs increased beyond 100, implying that the deep learning parameters overfit after 100 epochs. And the right graph shows the difference by the number of nodes. From this graph, varying the node size did not influence the performance significantly, but found that node size of equal 256 in either node yielded worse results than those with the smaller nodes. So as a conclusion, we developed a model that improves estimation performance of the future pharmaceutical sales from patents and pharmaceutical-related articles. And just using the words in patent yielded much better estimation than using the company name and the years of the first patent was applied for. And estimation performance was best by combination of the company name, was in patents, and pharmaceutical-related articles. And these imply that the patent and related article would contain future sales information. And as a future work, we'd like to apply the NLP while taking the structure of the patent and articles into the consideration. We would also like to examine the use of the word embedding concepts such as word and or word-to-vec to determine smaller words, similar words usage between patents and articles, and see how this concept improves the estimation performance. We also would like to apply to other industries such as food, electrical appearance, and cars, clothes, and so on. So thank you very much.